stated it was that what you recover is a set, u prime I, v prime I, w prime I, which there's a matching of, I never know which one is I equals 1, which one's I equals 2. So there was some matching of my factors, the order of my factors to the true factors, and then some rescalings that I actually recover the true decomposition. So the way that you can think about this is that you recover the set of rank 1 tensors in the decomposition uniquely. So that's the key point, is that you may not know which one is I equals 1, which one's I equals 2, but you recover the set uniquely. And because the rescalings which we talked about were just ones which preserve the rank 1 term itself, you could multiply this by an alpha I, and this by a beta I, and this by a gamma I, as long as the product of those factors is 1. And that was the uniqueness conditions. You could think about it as saying that we recover the rank 1 piece in this decomposition uniquely. Right? All right, so the other thing I want to say is that, before we move on to phylogenetic reconstruction, actually, maybe let me say one thing to address your question about, higher order, tensors. So one of the things you can do is imagine that I had a tensor which was 6th order. So it was, ui tensor, u prime I tensor, vi tensor, vi prime, tensor, wi tensor, wi prime. So then actually you can think about it as there's a way to flatten this decomposition into some new vectors. So you think about this as there's a way to define, this is called the Cauchy-Rao product. So imagine that ui and u prime I are vectors in Rn. Then what you're going to do is you're going to define a length n squared vector in the natural way. So what you're going to do is you're going to have ui1, need a bit more space, u prime I 1, ui1, u prime I2, and so on. So you can define some vector in n squared dimensions, which is really just taking the outer product of these two vectors, treating them as a matrix, and then flattening the matrix. And the important point is that from T, you can actually flatten it to get some new tensor, S, on some new factors. So the point is that what you can do is you can take a 6th order tensor, which is the sum of these 6 outer products. And there's a way, just from looking at the entries of that tensor, think about it in a simple case. If I give you a matrix, which you can think of as u tensor u, well, you can flatten it to get something which is a long vector, which is the Cauchy-Rao product of those two vectors, just by rearranging the entries. The same way that you can take a fourth order tensor and you can flatten it to, instead of getting an n by n by n by n tensor, you get an n squared by n squared matrix. And the same way I could take a sixth order tensor, which, each of these vectors are now length n, and I can create a third order tensor, again by rearranging its entries, where the vectors, the dimensions that we have, are each n squared. So now you have that the factors are ui, Cauchy-Rao with ui prime. So that's the key point, is that if you remember in Jenrick's algorithm, the crucial thing you need here is that the columns of u should for sure be linearly independent. Otherwise, there's no way you can recover them, and take something like the pseudo-inverse of them and for it to be well defined, right? So the key point is that while that puts an upper bound on how large you can hope to apply Jenrick's algorithm, because you can only choose R to be at most n, what if you think about doing sixth order tensors? Well, in principle, you can get R to be n squared. And you can still have a set of n squared vectors, ui prime, which their Cauchy-Rao products are linearly independent. In fact, if you choose these vectors randomly, that'll almost surely be the case again. So that's the key point, is that, to answer your question, not only can you apply Jenrick on higher order tensors, you get this uniqueness once you move from 2 to 3, but you keep having it at 4 and 5 and 6. But as soon as you go to high enough powers, you can actually get beyond what the naive limitations of Jenrick's algorithm would be. Instead of applying it in settings where R is at most n, you can hope to apply it in settings where R is at most n squared. And you can extend this in the natural way to sort of, flattening a ninth order one to get n cubed and so on. So that's the basic idea. Any other questions about tensor decompositions in terms of the algorithms? All right, so let's do phylogenetic reconstruction. So this is a bit of a long one. We're going to do phylogenetic reconstruction and HMMs. So it might bleed over into next time, but let's start it anyway. It's a really cool topic. We need all the board space I can get. And this is the motivating question that we're going to be interested in. Are there any computational biologists in the room? All right, so don't call me on any of my, this is all the computational biology I know. All right, so this is at least one of the interesting questions in phylogenetic reconstruction. I'll explain the model, but it's interested in the following question. I get to use this cool phrase, the tree of life. So, the idea is, imagine we took all of the extant species, which just means still living, and, you can contrast it to extinct. So what if we had, for each extant species, we had a fully sequenced genome for it, and we also had the assumption that these sequences were aligned with each other. So the question is, can we use those aligned sequences to reconstruct the tree of life? So which species, where were the speciation events, and how did they diverge? So can we reconstruct all of them? So the way we're going to attack this question is we're going to define a stochastic model, which the tree of life will be hidden from us, but we're going to ask questions like, if we're given many samples from this tree, can we actually reconstruct its topology and the transition matrices on each of the edges? And just think of these as being measures of, how long the evolutionary branches were and how many mutations happened. alignments. So, we'll be interested in the following stochastic model. So there are going to be a few parts to this stochastic model. So first, the question is, what is the tree of life here? So it's a rooted binary tree with root R, not all the leaf nodes have the same depth. So it's a general binary tree, and the one to keep in mind throughout this discussion is, let's do something like this. So we have some root node R. That's sort of the origin of all of these species. And what we have are the leaves now. These are the extant species. And all the other ones are the extinct species. So the internal nodes represent species that have, at some point walked the face of the earth, but have now died out. So we can't actually observe what their sequences are, but for all of the leaves we can. We've sequenced them and we've aligned their sequences. So this is the tree that we want to construct. This will be used to generate samples from a stochastic model. So the remaining thing that we need to do is we need to define a stochastic model on this tree. Yep?
So what does it mean that the sequence is aligned?
So let me get into that in a second. What I want to do, that's a good question, because there are a lot of assumptions hidden under this model. The biggest one is that you're given aligned sequences. So I think one of the interesting questions in phylogenetic reconstruction is about very simple models that ask you, how could you accomplish this alignment? And there's some really big open questions there. But the first thing I want to do is I want to just take this tree for granted, define a stochastic model, and then I'll give an interpretation of what it means for each of the samples from it. But that should hopefully answer your question about what we mean by aligned here. So for now, let's just think about using this tree to generate samples from a stochastic model. So the other important feature of this is we have a set of states. And the canonical one you should think of here is just, ACGT. And so we're going to think about our stochastic model as defining for each node, internal or a leaf node, assigning one of the states in it. So we're going to define a stochastic model that does exactly that. So this is, the underlying tree and the underlying domain that we'll be interested in, sigma. You can consider, not just ACGT. You could also consider, for example, amino acids and proteins. You can define all sorts of models this way, but this is the general framework. And the last piece in our model is we want to define a Markov model on the tree. And there are two components to this. The first one is a distribution, pi r, on the state of the root. So we're going to have to get this Markov process started somehow. And the way that we're going to do it is we're going to fix what the state of the root is. And then we're going to propagate it based on some transition matrices on these edges to defining states for all of the nodes. So the root just gets this Markov process started. So the remaining part is we need to define the transition matrices, which allow us to take the state of the root and propagate it to states in the tree. So the way that we're going to do that is, for each edge UV, we're going to have some matrix PUV, that's our transition matrix, and the ij entry of this will just be defined as the probability that the state of V equals J conditioned on the state of U being I. And just to be clear, so here, S is our random function that maps vertices to points in sigma. So these are the components of the model. We have the tree, the domain, how to start our distribution off, and then how to propagate it. And so just to make sure we're on the same page, how would you sample from this? So each sample can be generated as follows. So the first thing that you do is you choose the state of the root. And in this case, you choose it according to pi r. So pi r is just some distribution on the k possibilities, the 4 possibilities for the root node. And then the remaining step, which you just repeat, if you have some node where its state is fixed already, and S of V is not yet fixed, and UV is an edge. So you just think about this model as propagating based on, you're going to iteratively fix what the different states are for the nodes and propagate it out like some sort of contagion. Well, we have some node U, which is fixed to sigma, which is in our alphabet, and S of V is not yet fixed. Then what you do is you just choose S of V from the distribution. That's given. So remember that all of these conditional probabilities are encoded into our transition matrices. So what we do is if, for example, the rows represent the states of U, we look at the row in P corresponding to sigma, because we've already fixed U to be sigma. And that row sums to 1 by virtue of it being a transition matrix. And what we do is we choose the state of V according to that distribution for that transition matrix. So what this does is it allows us to, given the tree, given the states, given the transition probabilities, what we're going to do is we're going to choose what S is. So we're going to fix what this random function is in terms of what state we assign to all of the different nodes. But the catch is that all we observe are the extant species. So we observe that configuration, and we have no knowledge about how they connect with each other, but we want to figure out how the different species are related. Which pairs of species are the most related and diverged the last, which pairs are the furthest, that kind of thing. So this is what we want to do with samples from this model. So does the sampling condition make sense? How we're going to be generating samples? And now to go back to your question, what is a sample from this model? So a sample from this model is we observe for all of these extant species some label from ACGT. So what we're thinking of is that if for each species we have a very long sequence from it, and that all of these sequences are aligned with each other, then each column represents a different sample from this model. So the ith location is just a sample from this model. You know, which of the species have an A, which have a C, which have a G, which have a T in the ith location is the ith sample. So the very big assumption here, I mean, there are a lot of them, but it's already a very interesting starting point for thinking about phylogenetic reconstruction. You know, one of the biggest issues is, where did you get your line sequences to begin with? And this model doesn't really account for things like inserting symbols or deleting symbols, because we're assuming that everything is aligned. But there are much more serious issues which are completely wide open in statistics and machine learning, where you have very stripped down models in which, you know, one of my favorite ones is trace reconstruction, but I've decided I'm not going to think about it for another 6 months or so. It's a very hard problem, but essentially what it comes down to is you have, you know, some string which generates just through deletions many other strings, and you want to align them in a way to figure out what their common reference point is. And that turns out to be a much more challenging problem, but this is the model that we're going to focus on for today. Any other questions about this? All right. So the last thing is that...
a quick question.
Yep.
So, does the directedness matter for the arrows?
That's a good question.
Okay.
So in fact, the assumption that we're going to make is, you know, which is standard here. And we're going to talk about later, you know, this is the type of assumption that will allow us to use Generick's algorithm, as you'll see. It'll also answer Brendo's question about, you know, does it matter the orientation and how we've rooted the tree? No. We're going to assume that the transition matrices are full rank. That's what we'll need for Generick's algorithm to be useful. But we're going to talk about later, you know, when we talk about phylogenetic reconstruction and then later HMMs and noisy parity, we're going to see that actually when you drop these types of problems, the problem really becomes very different. It really does become hard, and people start to base crypto systems even on it. But for now, what we're going to assume that the PUVs are full rank. And actually, it turns out that when these transition matrices are full rank, what you can do is you can actually root the tree arbitrarily. So if you give me such a model where it's rooted in some way, and it has, you know, based on your choice of its root, there is some distribution pi r that starts it off. Well, it turns out that if all the transition matrices are full rank, what you can do is you can pick any other root r prime, and you can define some other model, you know, with pi of r prime, which starts it off, and some new transition matrices that are also full rank, that itself generates the same model. So it'll be exactly the same model. So that's something is that, you know, when you have full rank transition matrices, you can actually think about the tree as being rooted arbitrarily, but it's the same type of condition that we're going to need for applying Generick's algorithm anyways, because if you think about it, in Generick's algorithm, we needed that, for example, the UIs were linearly independent, and these UIs will come from, you know, rows in our transition matrices. So this condition not only helps you root the thing arbitrarily, but it's going to help you apply Generick to begin with. All right, so you know, there are actually two parts to this. So the two parts that we're going to focus on, and probably we're only going to get to the first one today, is first we want to find the topology. I can tell you about some of the classic work in, you know, evolutionary biology there by Steele and others. And then once we've found the topology, then it'll turn out that we'll be able to use tensor decompositions to find the PUVs, to find the transition matrices. So we're only going to use tensor decompositions in the second part, but let me tell you something about how you can actually go about finding the topology in its own way. And that's what we'll mostly focus on today. So our main goal is finding the topology. For the time being. And so there's been a lot of cool work on this. What we're going to do is we're going to follow the approach of Steele, very famous mathematical evolutionary biologist. And the algorithm actually came from Erdős, Steele, Székely, and Warnow. Actually, this is a different Erdős. It's kind of funny. I don't know. Anyways, right. So the basic idea is we're going to take our tree, which we don't know, and what we're going to do is we're going to define exactly the right metric on it. So we're going to define some metric on the edges, and that'll induce a shortest path metric between any pair of nodes, in particular between any pair of leaf nodes. But it'll be a metric which we can compute, at least given random samples, we can approximate it. And we're going to use this magical metric introduced by Steele as a measure of how near or far two different nodes are in the stochastic process, how much they influence each other. And we're going to use that to recover the topology with some simple combinatorial tests. So that'll be the first part. And then in the second part, which we'll probably only get to next time, is once we know the topology, we'll think about how we can construct a tensor that represents moments from our distribution. And the short version is that once we have this tree figured out, imagine I think about rooting the tree here. I can think about these three leaves as being conditionally dependent once I fix this guy. So that's exactly where we're going to get our three views that give us a tensor problem. We'll be looking at the conditional distribution of these three leaves conditioned on this hidden state, and that'll allow us, under the types of conditions we assumed, using Jenrick's algorithm to actually find the transition matrices. One of the, I mentioned at some point that Jenrick's algorithm has, to my count, been rediscovered in, I think, every decade since the 70s. One of the rediscoveries is actually in the context of evolutionary biology, so sometimes you'll hear this called Chang's lemma. Chang applied it to things like, can you even, given many samples, uniquely determine what the parameters are? And even did it algorithmically, and Mossel and Rock were some of the first to actually make that rigorous in terms of sample complexity and running time. All right, so what we're working towards is we're working towards a distance measure defined by Steele. And so what we're going to do to that end is we're going to let Fij AB be the probability that S of A equals I, S of B equals J. So this is just a slight difference than our transition matrices, because instead of having pairwise conditional distributions, we just have pairwise distributions. So this definition makes sense for any pair of nodes, internal or external leaves. But the important point is for leaves, we can actually measure these probabilities. So we'll be able to get good approximations to this matrix. And we're going to use this matrix to define our metric. So now the idea is what we're going to do is we're going to let phi of AB be defined as minus log magnitude determinant of FAB. So this is actually one crucial place where we're using the fact that the transition matrices are full rank. Because otherwise, it could happen that these determinants would end up being 0. Yep.
Is it obvious that the conditional matrix being full rank implies that this matrix is full rank?
FAB?
Right, so we originally, didn't
Yep.
we just want this like PUV to be full rank?
Yep.
Where we have conditional probabilities?
Yep.
Is that
Yep.
the same thing as
It is. That actually is very related to the idea that when you have full rank transition matrices, you can reroute the tree. So it'll actually come in that you can think about routing it to one of the leaves, and then you think about the transition matrices going there. But let me give a little bit more insight in a second, which is, the key thing that Steele showed was that this admits a nice description in terms of shortest paths along the tree that we wish we had access to. So the idea was that Steele showed phi AB is equal to the sum What he showed was that if we go back to our original tree, and we have two different nodes, U and V, well, for sure, since it's a tree, there's a unique path that doesn't hit itself again that connects them. It's the shortest path, where we just follow the tree to get from U to V. And we showed is if we let PAB, oops, I have it as AB here. If we let PAB be the path between them, which in this case is just this set of edges, then he said that phi AB can be decomposed as a sum of new UV, where UV are edges along the path. So that whatever this phi AB is could be expressed as just the sum of some values along this path connecting. And let's see. Now you can see why I'm not going to prove this for you. This is what his new is. But let me give you some intuition about this. Okay, so the key point here is if you think about when you're walking along this tree, as you're going from A to B, well, as I said, you can think about routing this tree under the conditions we talked about arbitrarily. So what if you rooted at A? Then you have some pi A marginal distribution, which you should be using for A. And then you start off with that distribution, and then you multiply it by these transition matrices along this path to get to what pi B should be, what the marginal distribution on B should be. Now, the important point is that if you think about the determinant of a product of matrices, it's the product of determinants. So what he's really doing here is he's exploiting that fact that you should think about this aggregate function, which is the log of some determinant, which you should think about morally as being the product of those transition matrices, as being the sum of the log debts along that path. Now you have to be careful because the same way there are these marginal distributions which also affect how you should define this metric. And the same way you need to add in extra correction terms, but these are things that telescope along the path. And that when you actually add this up along the path, it's not hard to show that this condition is true. So this follows just from exploiting the telescoping properties and figuring out what it looks like at the endpoints, that indeed this equation holds. But there's another assumption which is actually hidden under here, which is actually his main theorem. Any idea what other thing I should prove about this? It's not obvious by any means. So here all we did was we took something which we could measure, at least approximate, and we gave it some nice additive description based on these new UVs along the path. Where these new UVs happen to have this property, that we sure want the log det of PUV, because we have this property that the determinant of the product of matrices is the product of the determinants, and we add logs in there, they add up. And we have some telescoping terms to correct for the marginals at each of the internal nodes. But what I claim is not obvious is that this is a metric to begin with. So actually, Steele's main theorem is just that nu UV is non-negative. Not obvious at all. And actually, nu UV is strictly greater than 0 if all the transition matrices are full rank. So what this is this is a very nice metric that we don't have access to because we can't measure nu UV. We don't observe, for U and V being internal nodes, we don't observe what the pairwise distribution on their states is. So we can't directly compute it, even though it's a property of the model. But the important point is just the fact that we can measure these phi ABs is enough, and the fact that it has such a description in terms of a shortest path metric on the tree for some distance function is enough then to actually recover the topology of the tree, and that's what I'm going to show you. Does that make sense? So for right now, what we're going to assume is we're going to assume we have access to phi AB for leaf nodes A and B. In reality, though, you should keep this in mind that what we have access to are noisy approximations to this. So what I'm going to show you is the idealized algorithm where you actually had access to phi AB, but really the harder work in this Erdős et al. Paper is in showing that even when you only get a small number of samples, some polynomial number of samples, that your noisy approximations to phi AB are good enough to be able to do what I'm about to tell you. But for now, let's think about if we have exact access to this, how can we reconstruct the tree? Make sense? Any questions about this? So the key idea is to use what are called quartet fits. So imagine that we have leaf nodes A, B, C, and D. So the key point is that what we can do is we can take those 4 leaf nodes and we can look at the shortest paths between them. If we took the shortest path from A to B, or from A to C, or A to D, or any of the other pairs, then what if we deleted all the edges which are not on shortest paths? In general, what we're going to get is we're going to get something that looks like this. When we take all of the shortest paths and we delete all the edges in the tree that don't have anything, that don't participate in any of the pairwise shortest paths, we're going to be left with something like this. And we can actually think about this in a simpler way based on what its topology is. because we can ignore these internal nodes here and just think about how the shortest paths connect to each other. So here I'm deleting this node, or I'm contracting it, because it doesn't really affect what the picture looks like from a high level. The important point is that A and B merge with each other before they reach the other shortest paths. So the same way, there are actually 3 topologies that you can get. And there are only 3 because we're working with binary trees. So it's not really possible that A, B, and C simultaneously merge at one node, but they have to merge at different times. So there'll be some pair of nodes which joins before they reach any of the other shortest paths. And there are three choices for what this topology is. So I claim those are the 3 topologies, yep.
Have we used the fact that the tree is binary before in the previous?
No. No. And so the other thing is that binary is not really a restriction in terms of what I could do is I could put the identity matrix along there. And then in reality, I have sort of a 0-length branch and I connect things up. All right, maybe it should be new 0 if all the transition HCs are. All right, but any ideas about how we can actually, so what if we have these 4 leaves? And now what we're allowed to do is we have access to phi, AB or AC or AD and so on. So for all the pairs, we can compute what their phi is. Any ideas about how to decide which of the topologies we're in?
Using the metric?
Yeah. Any idea about how to use the metric?
The distance?
So let me put it this way. What distinguishes this from this in terms of pairwise distances between leaf nodes?
Distance between A and B.
Yeah. Okay. Yes? What would you want to say about the distance between A and B?
I guess if you compare distance AB plus distance CD to distance AD
Yes,
plus distance BC.
exactly. So you can't say that AB is the shortest distance. I could have put a really long distance on here, right? So you don't a priori know which is the shortest distance, but something you do know is that this distance is strictly greater than 0 under reasonable conditions. So what this means then is that if I think about the distance between A and B here, and add in the distance between C and D, they cover all of the edges except this one. But if instead in this diagram I looked at the distance between A and B and C and D, they not only cover these 4 edges exactly once, but instead of covering this 0 times, it covers it twice. So one of the distinctions here is not about a single pair, but when you add up, what you're really saying is that A and B should be treated together and C and D should be treated together. And the way that you know that is by comparing their pairwise distances. So the key lemma in here, let me state it more precisely. So the topology restricted to A, B, C, and D is exactly the one on the left and not the other two diagrams, if and only if. Now this is actually, though, assuming nu uv greater than 0 for all nodes, internal or external. Well, then this holds if and only if phi AB plus phi CD is strictly less than the other two possibilities. So the point is that each one of these possibilities is defined by what the shortest sum of the pairs of distances should be. And this topology on the left is uniquely determined because the pairing of looking at A to B and C to D is the one that's strictly the smallest. Does this make sense? Any questions about this lemma? It's just a matter of counting the edges on the path, so it follows immediately. Now what I claim is that it also gives us a way, all of this assuming that we have exact access to the phi ABs, to recover the whole topology. So are there any ideas about how to recover the entire topology from these types of, this is called a quartet test. So you have the power that for any 4 leads, you can determine what the induced topology is. But I claim that that's actually enough to build up the topology of the entire tree. Any ideas? Yep.
If you added in 1 node at a time and the additional tests to locate it.
Uh-huh. Yeah, I think that's definitely on the right track. Let me ask a more tailored question, which is, there's, if you have a leaf A and you have a leaf B, you can wonder whether their parent is the same. So I claim that these quartet tests give you a simple way to answer at least the question, should A and B be paired together in the tree in the sense that their parent is the same? So I think you were getting towards that, and that's definitely the right way to go. So any ideas for a condition which A and B should really be paired together?
This is a little brutal, but you could say for every other C and D,
Yep.
A and B are adjacent to the dotted.
Yep. Exactly. I mean, there's better ways to do this, but this is the easiest way to actually think about it. So there are a bunch of papers on trying to build up from quartet tests more efficient ways to find the actual topology. But if you just care about the qualitative question of are quartet tests enough to build up the topology, then it's kind of easy to see that you can do this. Because what you do is you look at all other leaf nodes, C and D. So this is the key point, is that, A and B, they really do, you're asking the question of whether this edge in this diagram represents a path that really is just an edge because A and B share a common parent. If they share a common parent, they can never be split. It's always the case that when you trace back their shortest paths, they merge before they meet anything else along the way. And conversely, if they weren't, if they didn't have the same parent, then whoever A's brother should be would be one which, when you do the query, you would get a different topology, where those two would be paired. So that's the key point, is that from these quartet tests, you can build up which pairs of leaves should be paired together. And now you can think about higher level things, like once you've paired up the leaves in terms of who have common parents, you can think about pairing up the pairs of those leaves in terms of which ones have a common grandparent, and so on. So you can actually build up the entire tree topology from this. So the last thing I want to sort of say, I don't want to get into all of the details of the sample complexity analysis for these things because it gets very tedious. But hidden in all of this is the assumption that I have access to phi AB, right? Which, if you remember what phi AB is, I think I saved it. So phi AB is something which we have this FAB, which is just the pairwise distribution. For those two pairs of nodes, what's the joint distribution over their states? And then what we do is we look at the determinant between these guys. Now, one thing I want to point out, this is something that was sort of hidden in the discussion, is that, what if FAB is the identity matrix? So in fact, what that means is that A and B always have the same state, and they really should just be treated as the same node. You can think about that as being like a branch in the tree which has zero distance between them. Well, then what we'd end up getting is we'd end up getting the determinant of the identity as 1, and then we get 0 for this, right? So the cases where we have 0 for this distance really does correspond intuitively to 0 evolutionary distance, that these two nodes have the same distribution and are always coupled to each other. But in any case, what you can notice from this is that the further nodes are apart, the smaller that the smaller this determinant is going to be, the larger the distance will be. So the same way that nodes whose joint distribution is the identity would end up having distance 0, things which are really far apart on the tree end up having really large distance. And that's not something that you can estimate with good confidence. So the real issue is, in all of this, I'll be describing some of the idealized algorithms, but you want to keep in mind what actually happens when you care about polynomial sample complexity. This is what Erdos et al. Did to try and make Steele's approach work, but what really ends up happening is that for really far apart pairs of leaves, you can't estimate their distance. So really what you want to do is you want to do quartet tests only over pairs of leaves which are somewhat close, which you have confidence over. So the question is, how can you build up the topology under just pairwise close quartet tests, and then reconstruct it from there? So that's the basic idea. So this Erdos et al. Paper is doing exactly that, and I'm not going to get into the details of it. And there are also a lot of technical conditions in even stating their theorem precisely. Because if you think about if you really did have one branch in this tree where the determinant was really close to 0, those are just two pieces of the tree. It cuts you into two subtrees, which really they don't have much relation to each other. So there's some conditions that you need to assume a lower bound on what these determinants are in order to get good sample complexity. And then in that paper, they go through all the laborious calculations of making these things work with reasonable sample complexity. So the last thing that I want to describe is to give you a bit of foreshadowing for what we're going to do next time. So remember that there are two pieces to phylogenetic reconstruction. The first one is how do you reconstruct the tree of life, which is what we did here, albeit we didn't talk about issues like sample complexity that get a little bit tedious. And then there's the question of once you have the tree of life, how can you actually reconstruct the transition matrices? Because you can think about this tree of life as only being a sort of crude approximation of what you really want to know. You may want to know in this tree how long are the different evolutionary branches. So that's something that's very crucial for understanding more than just how the different nodes connect up with each other, is how far apart they are and what time scale they represent the different speciation events. So that's actually what we're going to end up using the tensor decompositions for. So let me give you a little bit of a hint of that, and then we'll break for the day. So the real question here is, where are we going to find our tensors in this model, right? So you can think about it as, what if we had some tree that looked like this? It was just a very simple star, right? These could even represent paths, but that's not important. That's how we're really going to use it. So one of the things you can look at is you can look at the tensor TABC, which the IJK entry is defined as the probability that S of A equals I, S of B equals J, S of C equals K. So this is just some tensor, which we can estimate again from our samplers. So this is what I mean by saying, the natural way to use tensors is when you have samples from some stochastic model, where you're thinking of the tensor as arising from third-order moments. These are third-order moments because I'm considering the joint distributions of 3 nodes here. But the key point in applying tensor decompositions is not just using them for third-order moments that you can collect from your model, but you want to collect third-order moments which have a description as 3 conditionally independent random variables. So these are not 3 independent random variables, but conditioned on some hidden node, they are. Because in fact, in our stochastic model, when we choose what R is, from pi R, for example, then we can actually think about propagating what the state should be for A, B, C, and D independently. Because choosing R to be, for example, sigma, just means that in the PRA, the transition matrix from R to A, we're interested only in the row corresponding to sigma. And for PRB, we're only interested in the row corresponding to sigma, same with PRC. So we're just doing independent samples from those 3 rows. So these are our conditionally independent random variables. So what this means is we can give this term that we can collect, these third-order moments from our model, a new description in terms of the parameters we would like to learn. So what is that description? So we can think about it as sum over, the state sigma of the probability that S of R equals sigma times these conditionally independent random variables, probability of S of A equals something given, let's say, ijk, so So this is just from our model directly, that conditioned on this hidden state, what its state is. Everything else is conditionally independent. It is the product of these probabilities. But now you should be able to see that this is a tensor. This is a description of this tensor as a sum of rank 1 terms. This is just a scaling term, but this, as you range over I, and this as you range over j, and this as you range over k, is a rank 1 term because it's the outer product of 3 vectors. Right? So we can think about it this way. We can think about it as sum over sigma of this scaling term and then we take this transition matrix and we take its sigma rho. So the sigma rho of PRA, so the transition matrix from R to A. And then this itself, the tensor product with PRB, again the sigma rho, and then the tensor product with PRC, the sigma rho. So this is our tensor decomposition. And this is where things like, these represent the different rows in the transition matrix. So by assuming that the transition matrices are full rank, that's when we have the conditions of Jenrick's algorithm hold, is because of things like this. Right? And that allows us to say that from third order moments, we can algorithmically and uniquely determine what these parameters should be. These are particularly easy parameters to learn because we actually don't have scaling issues here, because we know that this row sums to 1. So whatever row we find, if it's a scalar multiple of this guy, then all we end up doing is we rescale it so that it sums to 1, and then we found it. And then we add in whatever scaling term we need to get the rank 1 factors to be equal. So that's the key idea, is how we're going to use tensor decompositions. I want to give you one more piece of foreshadowing, which is, if you think about Jenrick's algorithm, especially the way we talked about, I told you about this Khatri-Rao product too at the beginning, about how for 6th order tensors, you can get around these issues of only working with R at most n, the number of hidden states. Because the Khatri-Rao product will in general be linearly independent even when the vectors are not. But what I'm going to show you at the end of the next lecture is also a problem in learning called noisy parity. The classic open problem. People have started, it's so hard that people have started basing crypto systems on it. And it'll actually correspond to exactly one of these types of stochastic models, but with the key difference that the transition matrices are not full rank, the observation matrices are not full rank. So you should think about these full rank conditions as really being a crucial thing. It's not just a technical assumption, but it's something that when you don't assume it, you have to be very careful, because it can be that you contain hard models, which cryptographers really do believe are hard. So I think rumor has it the NSA also uses noisy parity as one of their test problems and stuff. So Jim Simons is apparently very interested in what the state of the art is in theory, but he was a little shocked that we haven't come up with better algorithms. So, all right, that's it for today.